Now we'll come to addition theorem on probability. So suppose we have two events A and B of a random experiment whose sample space is S. Then we can represent them using two intersecting circles. Now this is A and this is B. Now region in between A and B, it represents A intersection B. So this region, it is going to represent this probability A intersection B, which is event A and event B occur simultaneously. And if we look at this region, which contains either A or B, we say it is probability of A union B, which is at least one of A or B must occur. So loosely speaking, we say this is A and B and this is A or B. Now we know that N A union B is NA plus NB minus N A intersection B, and if we divide everything with NS, then we can simply write probability of A union B is probability of A plus probability of B minus probability of A intersection B. That is, probability of at least one of A or B is equal to probability of A plus probability of B minus probability of A and B. And this is called as addition theorem on probability. Now this addition theorem, it is for two events. We can write addition theorem for three events ABC. So this is our sample space and we have three events A, B and C. Then we can simply write probability of A union B union C, which is probability of at least one of A, B or C. And this is equal to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of C intersection A, and then plus probability of A intersection B intersection C. This is probability of A and B and C. All three of them, they occur simultaneously. We can write this formula in cyclic summation as this: summation PA minus summation P A intersection B plus P A intersection B intersection C. Now we can generalize this addition formula for n events. So if we have n events A1, A2, A3 and An, then probability of at least one of A1, A2 up to An, it will be this cyclic summation PAI minus summation PAI intersection AJ, where I is unequal to j, plus summation PAI intersection AJ intersection AK, where I is unequal to j, it is unequal to k, and it will continue up to -1 to the power n minus 1 probability of A1 intersection A2 intersection An. So this is called as addition theorem on probability. Now we'll discuss some conditions on two events A and B. So if A and B are two events, then we can represent them using Venn diagrams. This is sample space. This is your event A, and this is your event B. If we have to write probability of at least one of A or B, then we write this probability of A union B, and this region, it is region inside either or both of the two circles. Second one is both A and B. Probability of both A and B, or events A and B occur simultaneously. So in this case, we are looking for this probability of A intersection B, and this is the probability where we have this common region. So that's the probability of A intersection B. And from addition theorem, we have already studied P A union B is probability of A plus probability of B minus probability of A intersection B. Now this third one is probability that event A occurs but event B does not occur. So we can write A but not B. Now if we write A but not B, it is basically probability of A minus B, or probability of A intersection B naught. So basically here we are talking about that part of A which is common to B naught, or the part of A which is not common with B. So this is your sample space S. This is A, this is B, and when we say A but not B, that means A should occur but B should not occur. So here we are talking about this probability which can be represented by P A intersection B naught, and P intersection B naught is this probability of A minus this common probability minus probability of A intersection B. Now in the same way we can define B but not A. Now when we say B but not A, it is probability of B minus A, or simply probability of B intersection A naught. That is part of B that doesn't contain A. So we have this Venn diagram, and then we have A and B. Now we need B which doesn't contain A. So basically this region, and this probability is probability of B minus probability of A intersection B. Now fourth one is exactly one of A or B. That means we are talking about probability that either A occurs, B does not occur, or B occurs and A does not occur. That means we are talking about this probability of A minus B plus probability of B minus A, and it is probability of A intersection B naught plus probability of B intersection A naught. So here basically we are talking about region which is either completely in A but not in B, or region in B which is not in A. Now this is PA minus P intersection B, and this is PB minus P intersection B. So we can write this as PA plus PB minus 2 times P A intersection B. Or if we see this entire region is P A union B, and from P A union B we can take out this P A intersection B. So we can write this as P A union B minus P A intersection B. Now vis-a-vis union and intersection, we can say union of events, it is commutative. That means if we write P A union B, it is same as P B union A. In the same way, intersection is also commutative. So P A intersection B, it is same as P B intersection A. So they are commutative. Now this fifth one is neither A nor B. That means none of A or B must occur. Now we write this property as property of A naught intersection B naught. That is region which is common to both A naught and B naught. Now we can represent this region by this Venn diagram. This is A, B and S. Now A naught is region outside A and B naught is region outside B. Now the region which is common to both is region which doesn't lie in A or B. So if we need to find this property that neither A nor B occurs, this property is property of A naught intersection B naught, and from De Morgan's law and also from Venn diagram we can say it is complement of A union B. So this is property of A union B complement. So A naught intersection B naught, it is property of A union B naught. It is complement of A union B, and it is equal to 1 minus property of A union B. And sixth one is at least one of A or B must not occur. That means we are talking about probability of A naught union B naught, and again from De Morgan's law we can write this as probability of A intersection B naught or 1 minus probability of A intersection B. So another way to write this one is probability that A and B does not occur together. So basically this case is union of A naught and B naught or complement of A intersection B. So in this case is this entire region except for region in between A and B. So that's the case with property of A naught union B naught. Now using this definition we can further simplify these two. We can write probability of A intersection B naught as probability of B naught minus probability of A naught intersection B naught. Now if we look at this B naught, then B naught is this entire region, and that's our sample space S. This is event A and event B. And if we look at A naught intersection B naught, A naught intersection B naught is the region which lies outside of A and B. So from this we are subtracting this region which is outside of A and B. That means we are left with only this region which is same as A intersection B naught. So we can also write A intersection B naught as P B naught minus P A naught intersection B naught. In the same way we can write B intersection A naught as probability of A naught minus probability of A naught intersection B naught. So we can write it in terms of A and A intersection B. We can also write it in terms of B naught and A naught intersection B naught. So these are some of the cases with 2 events. Now we'll discuss some cases with 3 events A, B and C. Now if A, B and C are three events, then we can draw this Venn diagram. This is A, this is B, and this is C. Now the first one is probability that at least one of A, B or C must occur. So here we are talking about probability of A union B union C, and it is represented by this region. Second one is probability A, B and C all occur simultaneously. So this is given by probability of A intersection B intersection C. Now this is the region which is common to all the three circles. So this is A, B and C, and this region is probability of A intersection B intersection C. So basically we are talking about this region. It will be A but not B not C, or B but not A not C, or C but not A not B. Now this fourth one is exactly two of A, B, C occur. Now which two? It could be A and B but not C, or A and C but not B, or B and C but not A. So here we are talking about these three events A, B and C. Now this is A intersection B intersection C naught. That means the portion which is common to both A and B, which is this region A intersection B, which doesn't contain C. So we are looking for that part of A intersection B that doesn't contain C. That means we are talking about this part. This part is probability of A intersection B intersection C naught. This part is part common to A and C and which doesn't contain B, and this part is probability of B intersection C intersection A naught. And here in this first one, it was this region which is probability part of A that doesn't contain B or C. This is part of B that doesn't contain A or C, and this is part of C that doesn't contain A or B. And this fifth one is at least two of A, B and C occur. Now at least two is this case exactly 2, and exactly 2 is A intersection B intersection C naught plus A intersection C intersection B naught plus B intersection C intersection A naught plus this case when all three of them occur, and which is probability of A intersection B intersection C. So here it will be this region A, B, C, and this is sample space S, then this is exactly 2 of ABC. This last case, which is all three of them occur simultaneously. So while dealing with three events probability, we have this addition formula, which is probability of A union B union C, and which is equal to this cyclic summation probability of A minus probability of A intersection B plus probability of A intersection B intersection C. It is better to know all the regions. So if we have to write this region, that is the region of A which doesn't have B or C, we can simply write this region by this probability part of A that doesn't contain B and that doesn't contain C. So this is A intersection B naught intersection C naught. If we are talking about this region, it is nothing but this is simply A intersection B. So this is probability of A intersection B. Suppose we want this region. Now this region is region which is common to both B and C, which doesn't contain A. So this is probability of B intersection C intersection A naught. And if it is this region which is common to all the three, that is probability of A intersection B intersection C. And we already know A union B union C and all these associated regions. Now for three events A, B and C, we know union is associative. So probability of A union B union C, it is same as probability of A union B union C. In the same way, intersection is also associative. So it is A intersection B intersection C is same as probability of A intersection B intersection C. Now union and intersection, they also follow distributive law. So probability of A union B intersection C is probability of A union B intersection A union C, and probability of A intersection B union C as probability of A intersection B union A intersection C. So union and intersection, they follow commutative property, associative property and distributive property. So these are some cases with 2 or 3 event systems. Now here the question is, if M and N are 2 events, then which of the following represent the probability of occurrence of exactly one of them? Now probability of occurrence of exactly one of them is probability of M intersection N naught plus probability of M naught intersection N, which is M occurs, N does not occur, and N occurs and M does not occur, which is your option D. Now we can write this as PM minus P M intersection N, and the same way this is Pn minus P M intersection N, which is probability of M plus probability of N minus 2 times probability of M intersection N, which is your option A. Now another way of writing it can be, we can write this as probability of M naught minus probability of M naught intersection N naught, and the same way this is probability of M naught minus probability of M naught intersection N naught, and which is probability of M naught plus probability of M naught minus 2 times probability of M naught intersection N naught, and that's your option C. So the correct options are A, C and D. Now the question is, 3 numbers are chosen at random without replacement from 1 to 10. The probability that minimum of chosen number is 3 or their maximum is 7. So we have this event A in which minimum is 3 and B is this event when maximum is 7. We have to find probability of A union B. Now probability of A when minimum is 3, so we have one number which is 3 and then we need to choose 2 numbers which are greater than 3, which can be done in 7C2 ways. So it will be 7C2 upon 10C3 Now probability of B, maximum is 7. So we need to choose 2 from 1 to 6. So it will be 6C2 upon 10C3. And then probability of A intersection B, where we have minimum as 3 and maximum as 7. So in that case, we need to choose 1 from 3. So it will be this 3C1 upon 10C3. So we need to find this probability of A union B, and it will be 7C2. And 7C2 is 21 plus 6C2 is 15 minus 3 upon 10C2, which is 10, 9, 8 upon 3 into 2. So this is 3 and this is 4. So it will be this 120 and this is 12. So it will be this 33, which is basically 11 by 40. So answer to this question is 11 by 40. Now the question is, in a given race, the odds in favor of 4 horses A, B, C and D are 1:3, 1:4, 1:5 and 1:6. Assuming that a dead heat is impossible, find the chance that one of them wins the race. Now in this case, we are given probability of odds in favor. Now odds in favor is probability of A upon probability of A naught. Now if it is equal to A upon B, and if we use component to dividend, we can write probability of A upon probability of A plus probability of A naught, and there will be A upon A plus B. Now PA plus PA naught is 1. So from here we can write probability of A will be A upon A plus B. So in this case, probability of this horse A winning will be simply 1 by 1 plus 3. There will be 1 by 4. Probability for B will be 1 upon 1 plus 4, which is 5. Probability of C will be 1 by 6. And probability of D is 1 by 7. Now in this race, dead heat is impossible. That means no 2 horses can be winners simultaneously. So there has to be only one horse who is going to win the race. So in this case, this required probability that the winning horses, one of them will be given by probability of A union, B union, C union D, and it will be simply PA plus PB plus PC plus PD, which in this case is 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7, which is 319 upon 420, and that is the answer to this question. Now the question is, 2 cards are drawn from a well shuffled pack of 52 cards. Find the probability that one of them is a red card and the other is a queen. So one of the card, it must be a red card, and the other card, it should be a queen. Now we have 3 cases. First case, when we have no red queen. This second case, when we have two red queens, and this third case when we have exactly one red queen. Now if there is no red queen, that means we should have one red card out of 24 remaining red cards. So it will be 24C1 and then one queen which is not a red queen, and there will be 2C1 out of 52C2. Now plus. Now the second case is when both the cards are red and queen. So there will be simply 2C2 upon 52C2 and plus now one red queen. Now one red queen is simply 2C1 into other card. It can be either red or queen. So if it is queen, it is 2C1, and if it is red, it will be 24C1 out of 52C2. Now this is 48 plus 1, and here it will be 24 plus 2, 26. 26 into 2 is 52 divided by 52 into 51 divided by 2. Now this is 101 upon 1326. So this required probability is 101 upon 1326. Now here the question is, probability of A is 1 by 2 and probability of B is 2 by 3. Now we know that P A union B, it is always greater than or equal to maximum of PA and PB. Now maximum of P and PB is PB, so that means probability of A union B, it must be greater than or equal to 2 by 3, and we know that any probability is always less than or equal to 1. That means this option A, it is correct. Now if we look at A intersection B, we can write probability of A intersection B as probability of A plus probability of B minus probability of A union B, which is 7 by 6 minus probability of A union B. Now this value will be maximum when A union B is minimum, which is 2 by 3. So 7 by 6 minus 2 by 3, and there will be 7 minus 4, which is 1 by 2. So its maximum value will be 1 by 2, and it will be minimum when we put maximum value of P A union B, which is 1, which is 1 by 6. So this value will lie between 1 by 6 and 1 by 2. So that means option C is also correct. Now we look at this option B. This is probability of A intersection B naught, and it is probability of A minus probability of A intersection B. Now probability of A is 1 by 2 minus probability of A intersection B. Now it will have its maximum value when A intersection B is minimum. Its minimum value is 1 by 6. So if we put 1 by 2 minus 1 by 6, it will be 3 minus 1 by 6. So it will be simply 1 by 3. That means this option B is also correct. Now the same way we can write probability of A naught intersection B. Now probability of A naught intersection B, it is probability of B minus probability of A intersection B. Now probability of B is 2 by 3 minus A intersection B has two values, 1 by 6 and 1 by 2. Now we take 1 by 6, then it will be 1 by 2, which is its maximum value, and if we put 1 by 2, then it will be this 1 by 6. So that means all the four options A, B, C, D, they are correct. Question number 16 is, consider a large village where only two newspapers P1 and P2 are available to the families. It is known that proportion of families not taking P1 is 0.48. So probability that a family doesn't take P1 is 0.48. That means probability that family takes P1 will be 1 minus 0.48 and will be simply 0.52. In the same way, proportion of families not taking P2. So that is P2 naught, it is 0.58. That means probability that a family takes P2, it is 1 minus 0.58, will be 0.42. Now the next one is proportion of families taking only P2. So that means this is P2 intersection P1 naught. So we know that it is given by P2 minus P, P1 intersection P2, and this value is simply 0.30. Now probability of P2 is 0.42. So this is 0.42 minus probability of P1 intersection P2, and this is 0.30. So from here we can write P1 intersection P2 will be simply 0.12. Now we need to find the probability that a randomly chosen family from village takes only P1. So that means we have to find probability of P1 intersection P2 naught. So it will be probability of P1 minus probability of P1 intersection P2. So probability of P1, it is 0.52 minus probability of P1 intersection P2, it is 0.12. So it will be simply 0.40, and that's your option number C. Now here the question is, we are given PA, PB and PC, PA intersection B and PA intersection C, and PA intersection B intersection C. It says if probability of A union B union C is greater than or equal to 0.75, then show that probability of B intersection C lies in the interval 0.25 to 0.48. Now we know that probability of A union B union C is probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C, which we need to find, minus probability of A intersection C plus probability of A intersection B intersection C, which is 1.23 minus probability of B intersection C. Now we're given that probability of A union B union C is always greater than or equal to 0.75, and we also know that any probability is always less than or equal to 1. So this value, it is greater than 0.75 and will always be less than or equal to 1. Now this is minus 0.48 less than or equal to minus B intersection C, and will be less than minus 0.23. Now we multiply it with minus, inequality sign will reverse. So in that case, we'll get this x lying between 0.23 and 0.48, which is what we need to prove in this question. Now the question is, if A, B, C are three events such that probability of B is 3 by 4, A intersection B intersection C naught is 1 by 3, and A naught intersection B intersection C naught is 1 by 3, then probability of B intersection C is. So we have three events A, B, C. So this is A, B, and C. Now we are given that probability of B is 3 by 4. So probability of B is 3 by 4, which is this entire region. Now probability of A intersection B intersection C naught. So that means we are talking about that portion of A intersection B which doesn't contain C. So it is this portion. And this probability is 1 by 3. And probability of B intersection A naught and C naught. So that part of B which doesn't contain A and C. So we are talking about this region. So this probability is 1 by 3. Now we are supposed to find this probability. Now we know that sum of all these three will be equal to PB. So 3 by 4 equals 1 by 3 plus 1 by 3 plus probability of B intersection C. So probability of B intersection C will be 3 by 4 minus 2 by 3, which is 1 by 12, and that's your option A. Now here the question is, for three events A, B, and C, P exactly one of the event A or B occurs is equal to P exactly one of events B or C occurs equals P exactly one of events C or A occurs is P, and probably all the three events occur simultaneously is P square. Then the probability that at least one of the three events occurs is. Now we are given that exactly one of A or B. Now we know that probability exactly one of A or B, it is probability of A intersection B naught plus probability of A naught intersection B. It is given that this is P. Now we can write this as PA minus PA intersection B, and this is PB minus PA intersection B, and this is P. So from here we can write PA plus PB minus 2 times P A intersection B, it is P. In the same way we can write PB plus PC minus 2 times P B intersection C, it is also P, and also PC plus PA minus 2 times P A intersection C, it is P. Now if we add all these three, we can write 2 times PA plus PB plus PC minus P A intersection B minus P B intersection C minus P C intersection A, it is 3P. Now we have to find at least one of A, B, C must occur. Probability of A union B union C. Now this probability is PA plus PB plus PC minus P A intersection B minus B intersection C minus C intersection A plus probability of A intersection B intersection C. Now we already know this value. This is 3P by 2. So we can write this as 3P by 2, and intersection, all these three occur simultaneously. It is given in the question as P square. So this probability will be 2P square plus 3P by 2. Now question number 5 is, the carbonitrided bushes need to meet the specifications on surface finish, case depth, and dimensional variation. Otherwise, the bush is considered as a defective bush. Now we have a batch of 240 bushes, and out of them 30 do not meet the specification on surface finish. So the probability that the bush is not going to meet surface requirement is 30 by 240. And if it doesn't meet case depth requirement, that is PEC, probability is 15 by 240, and dimensional variation, suppose PD, will be 9 by 240. Now it says 6 on both surface and case. So that means this probability of S intersection C, it will be 6 by 240. Surface and dimensional S intersection D, it will be 4 by 240, and 4 on case depth and dimensional variation. So C intersection D is also 4 by 240. Now it says there is no bush not meeting specification for all three. So that means probability of S intersection C intersection D, it is 0. Now we need to find the chance that a bush randomly selected from the batch will be a defective bush. Now a bush will be defective if it has a problem in either surface finish or case depth or dimensional variation. Now this is equal to PS plus PC plus PD. So it will be 30 by 240 plus 15 by 240 plus 9 by 240, and then minus S intersection C, 6 by 240 minus 4 by 240 and minus 4 by 240 plus 0, and which comes to 40 by 240, and which is 1 by 6. So the chance that a bush randomly selected from the batch will be a defective bush will be 1 by 6. Here the question is, a probability that a student passes in mathematics, physics and chemistry are M, P and C respectively. Of these subjects, the student has a 75% chance of passing in at least one, 50% chance of passing in at least two, and 40% chance of passing in exactly two. Now which of the following relations are true? Now in at least one, it will be 1 minus, and he doesn't pass in any of the subjects. So it will be 1 minus M, 1 minus P and 1 minus C, and this probability is 75 by 100, which is 3 by 4. So from here we can write 1 minus M into 1 minus P into 1 minus C, and this value will be 1 by 4. Now we multiply it, we'll write 1 minus and then this summation M plus P plus C, and then plus this double summation M into P, and then minus M into P into C, and this value is 1 by 4. And this is the first equation. Now the second one says 50% chance of passing in at least 2. Now in at least 2, it will be this MP 1 minus C, PC 1 minus M, MC 1 minus P plus MPC, and this value is 1 by 2, and exactly 2 is this case. So it will be this MP 1 minus C, PC 1 minus M, MC 1 minus P, and this value is 40 by 100, which is 2 by 5. Now if we put this value in this second equation, we'll write M into P into C will be this 1 by 2 minus 2 by 5, which is simply 1 by 10. That means this option C is correct. Now from this third equation, we can write this summation MP minus 3 times PCM, it is equal to 2 by 5, and PCM is 1 by 10. So from here we can write this summation M into P will be 2 by 5 plus 3 by 10, and there will be 7 by 10, and that's our second equation. Now from here we'll find this summation M. So this summation M, it will be 1 plus, now MP is 7 by 10 minus MPC. Minus MPC is 1 by 10 and then minus 1 by 4. So it will be this 1 plus, and this is 6 by 10, and 6 by 10 is 3 by 5. So it will be 1 plus 3 by 5 minus 1 by 4. Now this is 20. 20 plus 12 minus 5, and there will be 27 divided by 20. So the value of M plus P plus C is 27 by 20, and that's your option B. Here the question is, there are 3 different pair of shoes in a lot. Now 3 persons come and pick the shoes randomly. Let P be the probability that no one is able to wear shoes. We need to find the value of 13P upon 4 minus P. Now let us say there are 3 people, P, Q and R. What we'll do is, we'll find the probability that at least one of them gets a matching pair. So we'll find this probability that at least one of P, Q or R gets a matching pair. So now this is this summation probability, one of them gets it, minus this probability 2 of them gets a matching pair, and plus this probability all of them they get the matching pair. Now probability that P gets a matching pair, it is 3C1 divided by 6C2. Now this is 3 and this is 3 into 5. So it will be this 1 by 5, and will be same for Q and R. So this will be simply 3 by 5. Now both P and Q they get correct pair. So this probability P intersection Q. Now P chooses correct pair, so it is 1 by 5, and then Q also chooses the correct pair. Now Q chooses the correct pair, that means it should be 2C1 from 4C2. So it will be this 1 by 5 and then 2 and 3. So it will be this 1 by 15. So it should be this 3 into 1 by 15, and this third one is automatically same as 1 by 15. So basically this probability is 7 by 15. Now we need to find the probability that none of them gets a matching pair. So this probability will be complement of this given probability. So it will be 1 minus 7 by 15, and that is 8 by 15. Now once we have the value of P, we can calculate this expression. So it will be this 13 into 8 by 15 and 4 minus 8 by 15. So it will be this 13 into 8, and this is 60. 60 minus 8 is 52. Now this is 4 and 2. So answer to this question is simply 2. And this question, it says, in a study about a pandemic, data of 900 persons was collected. It is found that 190 persons has symptoms of fever, 220 persons had symptoms of cough, 220 persons had symptoms of breathing problems, 330 persons have symptoms of fever or cough or both, 350 have symptoms of cough or breathing or both, 340 have fever or breathing problems or both, and 30 persons have all 3 symptoms, fever, cough and breathing problems. Now if a person is chosen randomly from these 900 people, find the probability that person has at most one symptom. Now basically if you look at its Venn diagram, now suppose this is fever, cough and breathing problem. Now the person will have at most one symptom if that person doesn't belong to this region. So what we'll do is we'll solve this problem using complement. Now we are already given this value. This is 30. So N F intersection C intersection B. This is 30. Now we need to find F intersection C, C intersection B and B intersection F. Now N F intersection C will be NF plus NC minus N F union C. Now NF is 190, NC is 220 minus fever or cough, it is 330, which is nothing but 80. And the same way we'll find N C intersection B, it will be NC plus NB minus N C union B. Now, number of people coughing, 220. Breathing problems, 220 minus both 350. Now it will be 440 minus 350, which is 90. And if we look at N, F intersection B, it will be NF plus NB minus N F union B, and it will be 190 plus 220 minus fever and breathing 340, and this is 410 minus 340, and it will be 70. Now we need to find this probability that the person has at most one symptom. Now this probability that this person has at most one symptom, it will be 1 minus probability that we choose a person from this region. So it will be this F intersection C plus C intersection B plus F intersection B minus, now we have considered this region thrice. So we have to subtract it 2 times. So it will be 2 times 30 whole divided by 900. Now this is 1 minus 180 by 900. Now this is 1 minus 1 by 5, and which is 4 by 5. And 4 by 5 is 0.8. So answer to this question is 0.8. Now here the question is, let E, F and G be 3 events having probabilities 1 by 8, 1 by 6 and 1 by 4, and their intersection is 1 by 10. Then which of the following is correct? So we have 3 events E, F and G. So this is E, F and G. So let this be E, this is F, and let this be G. Now it is given that probability of E is 1 by 8, probability of F is 1 by 6, and probability of G is 1 by 4, and their intersection, it is given as 1 by 10. Then which of the following is correct? Now we know that probability of E intersection F will be less than or equal to minimum of probability of E and F, and in between E and F the smaller value is 1 by 8, so it will be always less than 1 by 8. In the same way, probability of F intersection G will be less than smaller value between F and G, which is 1 by 6, and the same way probability of E intersection G will be less than or equal to 1 by 8. Now if we look at probability of E union F union G, we know that this probability will always be less than probability of E plus probability of F plus probability of G. Now probability of E is 1 by 8, F is 1 by 6, and this is 1 by 4. Now this is 24, 3, 4 and 6. So it will be simply 13 by 24. So this probability of E union F union G, it is less than or equal to 13 by 24, and that's your option C. Now if we look at this probability, which is probability of E intersection F intersection G naught. Now probability of E intersection F intersection G naught is actually this probability. This probability is equal to probability of E intersection F minus probability of E intersection F intersection G. Now this is probability of E intersection F minus, and this probability it is 1 by 10. Now we know that probability of E intersection F, it is always less than or equal to 1 by 8. So its maximum value is 1 by 8. So it will always be less than or equal to 1 by 8 minus 1 by 10, which is 1 by 40. That means this option A is also correct. Now we look at this option B. Then option B is probability of E complement intersection F intersection G. Now it will again be probability of F intersection G minus probability of A intersection F intersection G. Now maximum value of F intersection G is 1 by 6. So it will always be less than or equal to 1 by 6 minus, and this intersection is 1 by 10. So it will be 4 by 60, which is 1 by 50. So that means this option B is also correct. Now if we look at this probability, which is E naught intersection F naught intersection G naught. So it will be this region, and this probability will be given by 1 minus probability of E union G union F. Now this probability will be minimum when this value is maximum. So it will always be greater than or equal to 1 minus 13 by 24, which is 11 by 24. So that means this option D is incorrect.